3.5 UWB. The prefix ultra in English is used to mean extreme. In this sense, UWB stands for ultra-wideband, and UWB communication can be defined as a method of transmitting information over an extremely wide frequency spectrum. In some ways, this can be seen as similar to the early wireless Morse code communication systems. Like most technologies, UWB was initially developed for military purposes. Since 1994, many core UWB technologies have been declassified, leading numerous companies in the United States to focus on its commercialization. UWB utilizes a bandwidth significantly wider than even the broadband communication used in CDMA systems. To transmit signals across such an extremely wide band, information bits must be spread modulated, using spreading signals with extremely short pulse widths. This spreading results in a very large processing gain. Having a massive processing gain means that effective communication is possible, even when the transmitted signal's output power is extremely low. Thus, it is highly useful for short-range communication that requires minimal power consumption. Fields where UWB technology can be applied include wireless home networking, short-range mobile communications, vehicle collision avoidance systems, and distance tracking systems. UWB systems communicate with very low power over a vast frequency range. By using ultra-narrow pulses in the nanosecond, is 10 to the power of -9 sec, or picosecond, is 10 to the power of -12 sec range. In the case of IS-95, a South Korean mobile communication network, the pulse width is approximately 0.8 microseconds. Therefore, UWB can be said to have a processing gain about 1,000 to 1,000,000 times greater than that of IS-95. This implies that UWB can achieve the same signal even when communicating with power that is only 1/1000th, or 1/1,000,000th, as strong as that of IS-95. This characteristic allows UWB to communicate by utilizing frequency bands already occupied by existing communication service networks. For example, UWB can transmit information across bands used by FM radio 88 to 108 MHz, CDMA cellular networks 824 to 894 MHz, and PCS services 1750 to 1870 MHz. Because the UWB signal level is solo across such a broad frequency range, a CDMA cellular network would perceive the UWB signal as mere background noise. Figure 3 to 7 presents a conceptual diagram of UWB Ultra. As illustrated in this figure, the frequency bands utilized by UWB are the same bands already in use by numerous other narrowband communication systems. However, UWB operates with a massive processing gain and transmits at an extremely low power level. Consequently, other communication systems are unable to even detect the presence of the UWB signal. 3.5.1 UWB signal. A system is defined as UWB Ultra if its fractional bandwidth, the occupied bandwidth measured at the point where power drops by 10 decibels from the center frequency, is at least 25% of the center frequency, or if its absolute bandwidth is 1.5 GHz or more, as shown in Figure 328. Considering that the bandwidth of an IS-95 CDMA signal is 1.25 MHz, and its fractional bandwidth is less than 1%, a UWB signal would appear significantly flat. In comparison, this implies that the power levels at the center and the edges are nearly identical, a shape that can only be achieved by using pulses with extremely short durations. While various pulse waveforms are used in UWB systems, a Gaussian monopulse waveform is commonly employed alongside modulation techniques such as ppm pulse position modulation. In this scheme, multiple monocycle pulses are assigned to a single bit, with one pulse sent per frame. Thus, one bit of information is transmitted over several frames. This is similar to CDMA, where information is spread across multiple frequency bands. For multiple access, each user is assigned a unique frequency hopping pattern, or a PN code. The structure of a UWB transceiver system is illustrated in Figure 3 to 9. At the transmitter, data is modulated via ppm and synchronized with a code generator pattern to produce the pulse waveform. This synchronization with the code generator is identical to the process of modulating a spread signal with a PN pattern in a CDMA system. Through these stages, the UWB signal is generated and transmitted. The receiver consists of a correlator, pulse waveform generator, timer, synchronization block, and code generator, and it demodulates the signal using the same code pattern employed during modulation. The most significant feature of a UWB modem is that it directly transmits the pulses generated by the waveform generator, thereby eliminating the need for complex up-down conversion, or intermediate frequency if stages. However, since the filter characteristics of the antenna determine the bandwidth of the outgoing signal, the frequency flatness of the antenna becomes a critical variable. The unique communication method of UWB gives rise to a new paradigm in telecommunications. Its most prominent advantage is the massive processing gain acquired from using an incredibly wide bandwidth, which translates to exceptional resistance against peripheral noise. This noise immunity means that normal communication is possible, even at power levels as low as the noise itself. Furthermore, another implication of using UWB with its high processing gain is that even an extremely high energy pulse, when spread across a wide spectrum, results in very low energy density per unit of spectrum. In practice, many devices employing UWB operate at low power. For instance, the communication method required by the Zigbee standard for short-range communication is UWB. As such, it is utilized for short-range applications that do not require high output power. To reiterate, the significance of UWB's large processing gain lies in the fact that even high-energy pulses can have minimal spectral energy density once they are spread over a broad bandwidth. Since UWB transmits pulse signals without carrier modulation, it does not require a carrier oscillator. Furthermore, because it does not engage in high-power communication, a linear power amplifier is also unnecessary. Additionally, the system can be relatively simple as it does not utilize an intermediate frequency if stage. Just as it took about 30 years from the introduction of spread spectrum theory in the 1960s, for commercial CDMA products to emerge in the 1990s, UWB faces similar limiting factors for development and commercial service. While transmitting information over an extremely wide bandwidth allows for very low power communication, it also necessitates an extremely fast spreading signal to spread the information. An extremely fast spreading signal consists of very sharp waveforms with incredibly narrow pulse widths. Consequently, the receiver must operate much faster than a CDMA receiver to acquire and track the synchronization of pulses that are narrower than those used in CDMA. Not only in synchronization but also in general signal processing, the development of highly sensitive processors is the key to advancing UWB technology. Furthermore, another challenge in developing UWB systems can be anticipated. Even if we assume there are no interference issues from sharing frequency bands with existing systems, the UWB signal, which resembles an impulse signal with high peak power, despite its low average power or disruptions in other electronic equipment. In fact, while UWB was once considered a candidate for 5G and our new radio communication methods, it was ultimately sidelined due to these aforementioned challenges.